So I think it's time to get started on here. So welcome everyone to our expert Q&A workshop on fan optimization. As I mentioned before we dive into it, please take a minute to set up the Zoom, adding your organization to your name, and we will be using the chat throughout this. So if you have any comments or questions that come up through the workshop, please feel free to use the chat. You can find the chat button in the Zoom toolbar at the bottom of your screen. So as a little bit of an opener question, if you could please, using a browser or phone, go to menti.com and enter the code that's shown on the screen. If you have a phone, you can just take a picture of the QR code to get there. And Helen will be putting the link to Menti in the chat for everyone as they join. We'll be using this a bit throughout the workshop. So if you get in there, just leave it open on the side and we'll get started. So seeing some of the responses coming in, what fan application are you looking to optimize? So how do you use fans in your facility? And is there a particular system or application of those fans that you're looking to optimize or get some energy savings out of? And we have some HVAC, makeup air units, demand control ventilation, underground ventilation, return air, downcast air, large industrial fans. All right, so we're getting some answers in there. So if anyone hasn't yet, please go ahead to menti.com and enter that code to put those questions in. And I think, we have a bunch of different applications coming in here, and some from industrial, heavy industrial, commercial buildings, institutional, hospitals. Fans are part of all of these systems. And I think what we're going to be looking at today is addressing questions and highlighting some examples from all these different sectors, these different applications. I think, Vern, you mentioned that, when it comes down to it, a lot of the principles and application around this, it's the same principles guiding those fan systems regardless of these applications. It just ends up looking a little bit different in practice. Is that your sort of take on it?
Oh, totally. Totally. A fan's a fan. They're all kind of behave the same way. They work the same way, and they're just different in terms of size and application.
All right. So thanks everyone for getting those questions in through Menti. And as I mentioned, today's focus, we're having an expert Q&A workshop on opportunities for fan systems. I'm Jay Mullen from the delivery partner for the Energy Manager Support Services through Save on Energy. And I'm very happy today to have with me Vern Martin from FlowCare Engineering as our expert Q&A for today's topic. I also have Helen and Alikia from Goldson, from our organization, helping out. So Ali will be manning the chat. So if you have any questions, feel free to enter those into the chat there. We may be able to answer those within the chat or raise them to the larger group. And if you have any technical assistance, Helen is our producer today to help out with that. So diving into it, before we get into it, I do want to mention, as a reminder, the Energy Manager Awards are coming up November 24th at the International Center. We're really excited about these. We've been delivering virtual remote sessions throughout this entire year. This is our first session that we get to do in person. So I'm really excited to see everyone there to celebrate the successes from energy managers and the great accomplishments that they've achieved. And also we will be having a panel with some energy managers that have achieved great success, focusing on what were some of their key success factors that led to those results and how they got those success factors in place. So as a quick reminder, space is limited on this being in person. We don't have that flexibility that we maybe have with the virtual events to accept anyone at any time. So please register now. There's a QR code on here, or you can contact us, and Helen will be sending, or has put the registration link in the chat if you haven't yet already. And today's agenda, quickly, we're going to talk a little bit about the fan system approach and how you look at your fan systems and what your considerations that should go into that for energy savings and other optimization. We'll be looking at some case studies and expert Q&A. Now, this isn't exactly linear. This is going to be kind of sprinkled throughout as we go along, but that's what we're looking to cover today. And we're going to start with a little systems approach to energy optimization. and getting into a little bit of what that means. But when it really comes down to it, it's focusing on fan power and energy. So we did send out a pre-work, a quick 3-page document with a little bit of background information. So we're going to start with a quick, quiz, because we know that's what everyone wants to be doing on a Tuesday morning. So a quick quiz to refresh some of the information that was in that and make sure that everyone's kind of on the same page with some of that foundational knowledge. So if you could go back to Menti that you had open from before, again, you can go to menti.com on your phone or browser and enter the code 53616406, or just follow the quiz or the link that Helen has put in the chat. And you should have a question there of what does it mean to take a systems approach to fan optimization? Does it mean using sensors and controls to reduce energy consumption? Does it mean focusing on minimizing energy consumption of all system components, or understanding how fans, ducts, filters, terminals, and other components work together? And we see some answers coming in there, and it looks like maybe we made these questions a little bit too easy on there. Because that last one is the correct answer on there, and it really is about looking at, from the inlet to the exhaust of your whole system, making sure that those understanding how all the components do work together. And I think, Vern, this is something that you really touch on and focus on in your presentation. Is that correct?
Totally. We'll be going from one end to the other, and even as part of the system approach, it's the methodology of doing this. So yes, absolutely.
All right. So moving on to our next question, how can fan power consumption be reduced? Can you reduce the fan power consumption by reducing flow, reducing pressure, increasing fan efficiency, or all of the above? So if you read the pre-work on there, and as we're going through, if you didn't have a chance to read that pre-work, Helen will share the PDF in the meeting chat, and we'll also be sending it as part of the follow-up following the event. And again, we've got everyone sort of answering in there, and I think we may have made all these questions a little too easy. I think I'll have to get some trickier ones in next time.
Maybe everybody just did their homework.
Oh, that would be a first, right? Great. But yeah, those are, we saw those equations for fan power of flow times pressure divided by fan efficiency. So those are the main components. And as we mentioned, regardless of the fan system, industrial, commercial, those are the factors that are going to influence your fan power consumption. Moving on to our last question is, why do we use fan curves? Is it to quantify fan annual energy consumption, to choose an appropriate fan based on system characteristics, or to find opportunities to optimize system flow and pressure? Now, these are all good things to do with your fan system, but we did have a little bit of an introduction to fan curves in terms of their application and how to use them on that pre-work. So this one, we do actually have a little bit of a mix of responses on here. So we'll give a couple of seconds just to let those come in. Great. And there's a good mix going on there. So Vern, do you want to sort of reveal what we would consider the correct answer, or the shorthand correct answer for this?
I think both where people are putting their responses are correct. The one on the middle there seems to imply selection of a new fan, for which you obviously need to have the performance curve. But for an existing fan, it really is to understand what's going on with your system, and being able to define the flow pressure relationship of what's going on and how the fan interacts with the system. So I think both of these are probably fair responses.
Great. All right, so that's the end of our little quiz for this morning.
I will just say one thing, Jay. If you don't have a fan curve and you're trying to optimize a fan system, life gets miserable for you. You can do it. You can do it. And there's there's like anything out there, there's workarounds for things. But boy, life gets a lot easier when you've got a document in front of you that you can look at and say, okay, so I know what this fan's supposed to be able to do, and now I know
Right.
what to do with that.
All right. So an excellent starting point on there. All right. So getting back into it, I'll hand it over to Vern to talk a little bit more about that systems approach and finding the power and energy reduction opportunities.
Well, thanks, Jay. I'll guess I'll dive into it here. For those who don't know me, I work for FlowCare Engineering, and I prior to FlowCare, I worked for a fan company that did fan troubleshooting work, and then prior to that, I actually did work for a fan manufacturer. FlowCare is still does the troubleshooting work. We do energy optimization work. We do computational fluid dynamics analysis. All of these things. We do not sell fans. We don't have a relationship or a association with a fan manufacturer or fan distributor. And I want to make that point kind of clear at the outset. We're strictly fan consultants and have been doing this since the early 90s. I want to mention one thing here, that there's a lot of questions that I did get a chance to get a quick look at in advance here. And if I don't get to a question, or answer it quite well enough, I'll be more than happy to make myself available at any point after the presentation. There are a few questions that start getting into some very specific application issues for which I may not be the right person, and I'll identify that once we get to that point. Okay, next. Oh, where I haven't spoke to this slide yet. Okay, so power and energy reduction opportunities. Okay, so let's start with the big picture here of where do we start with this task of trying to optimize a fan system? What are the potential areas to investigate? Well, we know one thing, that there are only 4 ways that you can reduce energy on a fan at a fundamental level. And the first is to reduce the flow. The second is to reduce the pressure. The third is to increase the fan efficiency. And the last is to play with some timing issues there, because energy is a function of power times time. So when I look at a fan system, and I kind of lay it out like this. We know that we got electrical power coming in. We may have some efficiency aspects to the power coming in. It may be going through a VFD, where there'd be a bit of an efficiency loss. It's coming into the motor. There's a bit of an efficiency loss, but at some point we're going to have a motor that's turned electrical power into mechanical power, and it's driving a fan. Now, the fan efficiency, like any other efficiency, is a ratio of output to input. The output of the fan being its let me get myself set up here with this ratio of the output to the input, and the output is pressure and flow, and the input is mechanical power. And so if you're looking, but within each one of these, there's some variation and so on with this. So with the pressure, you could look at some of that as being variable and some of it being fixed, and we can think of lots of examples of that. With flow, we got productive uses and non-productive uses. So if a fan's delivering a certain amount of flow, it's going into the the conditioning space, or it's being used in some industrial environment. It's got a purpose. There's a productive use. Okay, so if there's a whole lot of leaks in the ductwork, that would be non-productive use. The fan's still moving the air, but now you're moving air that no longer provides a useful function. Same sort of thing happens with the pressure. You work through all the pressure losses of a system, and that really doesn't change. Those are our fixed losses. And then beyond that, we have the variable losses. If the filter is getting dirty, that is a variable loss. So all of those things play a role in how one establishes how you go about looking at these areas to investigate. So the very first thing that you look at is deliver what is required for the system. No more, no less. There's no coins that get delivered to you for giving the system more than it should have. The second rule is to streamline the delivery path, okay? So if you've got all kinds of twists and turns that make it that much more difficult for the air to get from A to B, then you're going to need more pressure. And so that then becomes becomes an energy requirement. The third is to have an efficient fan, which we'll get into that part of this. And the last is to match the demand efficiently. Now, what's implied with rule 4 here is that a fan doesn't just have one operating point. Fans may have one operating point, but more likely it has a whole range of operating points. And that happens if no matter whether you're dealing with an HVAC system or an industrial system, and some have more, some have less. I was working with a cement plant the other day, and doggone it, most of those are pretty flat. But on a steel plant, which is batch operated, well, all of a sudden you've got a bunch of things happening. You need all kinds of fume collection going on, and then things settle down, and then you don't need hardly any movement of flow at all. And that then gets into something that we call the load duty cycle for a system. Running that relationship between how much time you need something and what you need it for, whether you need it for a full capacity, a mid capacity, high capacity, or anything in between. Okay, next, Jay. So a system approach. Now that word system is an interesting word, because system means, on one level, it means you're doing something in a methodical sort of way. And on another level, it kind of has this implication that it's beyond the fan. You're into the system part of this. And both of those are certainly applicable as far as using that terminology of something being a system approach. Now, when you look at a system and you're trying to figure out where are my efficiencies and inefficiencies with this, you have to remember that things can have started and maybe have gone wrong right from the very beginning when the system was designed. Somebody put this system together, and then the second part of this, they selected the wrong fan for the equipment, and they're still struggling with that decision that was made at the design stage. And then you get into things like maintenance and the operation of the equipment, and literally things can go wrong at every one of the stages with this, as far as understanding what this relationship is between what the fan's required to do and what the system really requires. I'm going to throw this question out to the group here, which is, and Jay touched on this in an earlier point here, where we're looking at the different ways that we can reduce energy in a system. But there's this question that comes into play here, which is the easiest to reduce? And I'll let you think about that. But we know that, as I said, efficiency is output over input, and flow times pressure divided by power. So two of those variables are in the numerator and one's in the denominator, but let's just ignore that. If you're going to reduce by 10%, let's just say the impact of each one of those is almost the same. So which is easier to reduce? If we want to drop our energy by 10%, is it easiest to do pressure losses, or is it easier to do flow? Reduce flow, or increase the efficiency? Because they all have the same impact. The other one, of course, that has similar impact is the element of time. Can we knock off our system, our fan off for 10% of the time? That also will reduce energy by 10%.
So we have a couple of responses in the chat from Benjamin and Max suggesting that reducing flow might be the easiest one.
Okay. Yeah. And you know what? Sometimes it is, but my experience in the industrial world, at least, is you try and tell your customer that you want to reduce flow. You know what he's going to tell you? Are you kidding me? I'm not going to reduce flow. You might even have problems with an HVAC system to convince your client you were going to reduce the flow. So that it might work, and in fact, it might work if you've got some already variable application there that works, but for the most part, that one gets pretty tough. Similarly, increasing efficiency by 10% gets pretty tough. Fans have been around since around 1850, industrial fans, and surprisingly enough, some of the most efficient fans that we've seen out there were built a long time ago, and I'll touch on that because there was a question that related to fan efficiency and what happens over time. But in my opinion, the easiest one of these is to reduce the pressure losses, because that one almost has no impact on what they're doing right now. Okay, if we can figure out how things went wrong from a pressure perspective and correct that, they've got a system now that will move the same amount of flow but with less pressure, and so that it's a very low impact thing. It might not be low impact to actually do, but it probably is quite low impact in terms of living with the decision on that. So I would pick reduce the pressure is probably the easiest from that perspective. So basics of fan selection, and we're going to get into a little bit of that because I know there's some questions, but if we're starting off with a system design, the very first thing that you're going to deal with is in fact, the flow, and establish what your flow requirements are. And establishing what your flow requirements means that your worst case scenario is satisfied. Whether or not that's a worst case for the amount of heat load that you've got rolling into through the glass on your office buildings, or the number of occupants, or trying to meet ASHRAE requirements, or if you're dealing with a process, no matter what that process is. So you got to establish your flow requirements, and establishing the flow requirements also means understanding what the range of those flow requirements are, because flow requirements isn't just one thing out there. It's a whole range of things that go right from what we would call idle mode to a full flow requirements. Now, once you've done that, you're into the issues of designing the hardware, and this graphic that you see in front of you is just an old-fashioned thing that helps people work through issues of pressure drops and resistance of ducting, and in the top right corner what the losses are around fittings and so on. But that's essentially what you're doing. You're figuring, okay, I got a process over here, and I'm going to move that gas, and it's got to be conditioned, or it's got to be cleaned, or it's got to be doing something in the process. And then after the process, it's got to be cleaned again with a scrubber, a bag house, or something else. And then eventually it all goes up a stack. So there's a whole hardware that has to be designed, and the pressure losses throughout the hardware get sorted out. And then from that, you prepare a fan spec.
Well, thanks for that setup on the systems approach there. I think that's really useful. What we're going to do now is start looking at each of those three components of reducing flow, pressure, increased efficiency. And I think, Vern, you've got a couple of slides on those that we'll get through quickly, and then address some of the questions that were submitted for each of those areas. So if anyone does have any further questions, please feel free to add them into the chat. So back over to you, Vern.
Thank you. I'll try and skip along a little faster. Meeting the flow requirements can mean just simply looking at relevant requirements, either what's specified by engineers on industrial projects, or maybe just some regulations that already apply, the ASHRAE standards. If you're dealing with a boiler, you've got air to fuel ratios that come into play. Mine ventilation is kind of interesting because the traditional way of sorting out how much flow that you want to move in a mine, it relates to the number of horsepower of diesel that you have. But in recent years, there's been a move towards doing things like what they call VOD, ventilation on demand. And so that would relate to moving the amount of air that satisfies various sensors in the mine, whether or not those sensors are temperature or carbon monoxide or dust or whatever else. Some of that works fine. Some of it doesn't work as well as you want. And so maybe you take a slightly lower view of what VOD actually means, and you start dealing with timing issues and so on. If you're dealing with a dust collector, you got to worry about fume capture velocity. And just for sake of interest here, what you're looking at that picture is what was, at least at the time, was the largest mine exhaust system in Canada at up north of Sudbury. Okay, next, Jay. So you want to eliminate unnecessary flow. As I talked about at the outset here, there's productive and non-productive flow. Closed duct runs when not needed. If you've got a fume collection system and you've got 100 different points where you can capture, but some of those aren't needed at any given time. Why have them all open? It's sort of like walking onto an aircraft and sitting down at your desk, at your seat, and everybody's vents are all wide open, and not all of the people in the plane may be wanting to have air blowing on them at a particular time. Institute controls to avoid venting and recirculation. And the last one on that list, don't oversupply the system. Those two, in fact, are slightly different, but they tie together in many ways, which has to do with the fact that quite often you end up with fans selected for worst case scenarios. Then when they're operating at what we would call their normal conditions, there's almost too much capacity there, and the fan can't be controlled, or it's unstable in some way. So a certain amount of air gets bled off essentially to make the fan stable. I'm going to touch on one of those in an example later on. Okay, Jay.
All right. So we've got a few questions that were submitted in advance from the audience, and a couple from Alan was, first off, if there's any methods you would recommend towards mitigating some of that infiltration, exfiltration that may occur in a system.
Well, I'm looking at that question, and I wasn't sure if it meant a system, or perhaps it means a whole building if it's an HVAC requirement or something like that. And the approaches for that are quite different. I mean, with a building, you typically want to have it as tight as you can because you want to control what's going on in the building. And if there's openings in the building, well, that's not a good thing. And all of a sudden you have uncontrolled either infiltration or exfiltration. If you're dealing with a system, yeah, go ahead.
Sorry, I was just going to say, Alan, if you want to make any clarifications on there, please feel free to add in the chat or unmute and let us know on that. But go ahead, Vern.
If we're dealing with a system, then we're dealing with leakage issues. And if you're going to try to mitigate the leakage issues, I'll just say one thing off the top here. It's easier to mitigate exfiltration, especially if you've got dusty air, than an infiltration, because you can see the dust that's coming out. That actually is a little wee bit of a problem. And to take a very short rabbit trail here, one of the issues with bag houses that the EPA south of the border here has done is in steel plants, they want to see all the bag houses in the future be on the clean side of the fans and be under negative pressure. And the reason why is because they don't like them leaking, and they don't want that dust coming out into the environment. The problem with this is that once upon a time, we could see that dust coming out into the environment, whereas now when they're all under negative pressure, leakage is coming in. You got no way of seeing that. So back to Alan's question and how to best to answer that. If you're going to try to deal with one of these two, infiltration or exfiltration, I guess you can test. If this is our ductwork from here to here, you test here and you test that there, and you kind of see whether or not you're coming up with the same values in order to establish whether or not you've got some infiltration or exfiltration between the 2 points. One of the things that I highly recommend people do in their systems is have a very good idea of what the pressure should be throughout their system. So when you got a system that's brand new, for a particular flow rate, it's tested, you go through your system and you go, okay, I know what the pressure is here and here and here and here. And then later on, as this system gets used and it's now, there's maybe erosion issues or wear issues or buildup issues and so forth, then you can kind of see how that changes over time. So I'm not sure if I'm down the right path with Alan's question.
Yeah, you've answered that, Vern. Thank you.
Okay. All right.
And then Alan had another one in terms of, if you having an exhaust fan with a VFD, which you mentioned, like controlling that flow so it meets demand is a great way to save energy. But in terms of how that VFD is controlled, tying it to either like a door open position or a VOC sensor, and any advice on that of controlling for the exhaust fans?
It's I used my mine example there a little bit about the VOD and some of the difficulties in knowing whether the sensors can pick it up adequately. And for a VOC, I'm not exactly sure what sensors are out there and what they can all do, but assuming that VOC sensors are adequate and they respond adequately, and you don't need so many in a space that they will in fact give you a good readout of or a reading of what the overall space is, that might be a good way to go. I guess the alternative is, as Alan has suggested here, you relate this to something with the door open and the door closed. And I'm assuming when the door is closed, because the VFD can take the fan down, and when the door is open, it can be triggered to crank up the speed in order to give you the evacuation you're looking for.
That's correct.
I think both of them have merit. I'm just not familiar enough to know what a VOC sensor means in terms of how quickly it can respond, how accurately it can give you what you're looking for, and so on.
So Vern, my concern on the door issue is not so much with the exhaust fan, but with the typical oversight of not looking at what other systems would be impacted by that. So what I mean by that, if you've got a building that make it a square box,
yeah,
the exhaust fan's taking air out of the building. If the door is closed and the fan is now on, where's that coming from? It's got to be coming from either infiltration or from another HVAC.
Yeah.
And what I'm finding is some of our engineers are really good at turning fans off or turning fans down, but not really good at figuring out what else in the system needs to be balanced.
Well, that's a good point. And I think one of the suggestions that kind of jumps out perhaps from what you're saying there is it needs another duct coming into this with another damper on it. And at the same time that the VOC sensor is triggering that, oh, we got to start evacuating, then that means that a damper has to open up into a ductwork at the same time that a fan speeds up. And then that way the door is kind of a non-issue with this. Something like that, right?
All right.
Okay.
Thanks. And then we had a question from Olga about how to determine if a washroom exhaust fan runs with not needed. And this would be in a commercial retail situation. And what would the cost be to tie the exhaust fan to the washroom motion sensors or occupancy sensors in there?
So the first part of that, how to determine if it runs when not needed, I guess it's like anything else out there, trying to get a trend on what's going on with it right now. And I'm not really I've never done that for a washroom exhaust fan, but I'm assuming that either electrically you can determine whether or not something is on or off, or perhaps with the pressure sensor. And you can get fairly inexpensive sensors that can make those determinations. What would the cost be to tie it to washroom motion sensors? Not really sure. It's a little out of my field. I don't think it would be very expensive. I mean, you can pick up sensors. I know the various sensors that are out there now that are part of various security systems. None of those are very expensive, and you'd need to have some way of using that and relaying that to tell it to turn washroom on and off. I do have one point I want to make with this question, Olga, that maybe you can enlighten me at some point after the discussion today. But, when I think of exhaust in buildings, whether or not it's an office building or a retail space, I'm assuming that most buildings are going to work on the basis that you're going to have supply fans, or you're going to have return or exhaust fans, and you're trying to keep your building at a particular pressure sensor, a particular point of what that pressure should be in the building, so it's not either too positive or too negative. But you always want to also be exhausting out of the building, in which case the logical place to exhaust a determined amount of air is out of the washrooms or out of some other area where you've either got high heat generation or other. I mean, in the olden days in office buildings, there was a reason why they used to put the photocopiers all near the washroom. It's because the washroom became that collecting point for exhausting a certain amount of air. So maybe I just need to know a little bit. I'm assuming this is a retail application, and I perhaps need to know a little bit more about how all of that typically works.
But I think, like Vern, to your point, that understanding of, are those washroom exhaust fans intended to just, evacuate washroom air, or are those the exhaust fans that are meant to serve the whole building, because that's
Yeah.
a different how you may want to be controlling it
Right.
on there, right?
I would say that's true. Yeah.
Okay, so I think we'll move on here, and we had one last question around the flow side of things, and it was, can you convert a constant volume rooftop unit to a variable volume while addressing TSSA issues, control issues, ASHRAE requirements, and control strategies? So I know we have a lot, both in industrial and commercial spaces, where they have those constant speed rooftop units and are looking to go to variable speed, but how do they address with those considerations of still meeting those different flow requirements laid out in guidelines or regulations?
Yeah, and I've never done it. And I mean, we got a rooftop unit right above my head here in our building, and can it be converted to variable volume and still address any of the safety issues? I think it can. I think most rooftop units can be converted. Okay, I don't think there's any doubt about that. The question is, do you want to do that, or does it make sense to do that? Does it economically make sense to do that? I mean, rooftop units, you're not spending hundreds of thousands of dollars. You might spend, if it's a small one, you might spend 5,000 or 10,000, maybe 20,000, depending on the sizing issues. Of course, that's something that is quite variable. But I have no doubt that you likely can do it. I think there's some tricky stuff with that, because you are dealing with combustion issues, and whether or not you can meet all those requirements easily, I'm not real sure. There is one point I want to make with this, and that is that you run into a bit of an issue where if you're looking at how much air you need to move in from purely a temperature perspective, that's one thing. But the other thing you have to keep in mind, and this is the one thing that you run into an issue of any kind of ventilation issue where it's occupants that you're trying to make comfortable, and that is that diffusers are above our head at the ceiling, and that air has to get down to the occupant. And if you start reducing the velocity of that air as it leaves the diffuser, you can run into this issue where the air gets short-circuited. It doesn't make it quite down as far as it should, and you don't have the mixing effect into the space. And if you don't have the mixing, what you might have is that air short circuits, and it gets pulled out by the return side of your system here before it should. So it becomes a little bit of a tricky issue, and I'm not quite sure. There's other science issues involved with that. Well,
and I think we've seen a number of these projects, but I think to your point, Vern, and what you mentioned before on that systems approach, is it starts with that understanding around what your flow requirements are. And that includes related to, the different regulations, or, what is happening in the space. Is there fumes that need to be evacuated even when people may not be present, and matching that. And then I think, working with the proper, the good installers on there, that to maintain that face velocity coming out of the diffusers, and make sure that you're still getting that proper mixing in place.
The key is there, you always want to make your processes satisfied. Well, in an HVAC system, we're the process. We're the ones that have to be satisfied. And very clearly, if that air is dropped down too much, then you might find that it's now colder, but it might come through and drop because of the density of the cold air will drop down. But you can run into some other issues with that. I'd want to be kind of careful with that.
All right. So we'll move on to reducing pressure. So Vern, I'll hand it back over to you for the ductwork design.
Sure. Thank you. So what you're looking at on that screen is a complicated ducting system for a steel plant, and in the industrial world, the big thing in the industrial world is having enough velocity that you can carry particulates away. And every process will be a little different if you're dealing with wood products or steel products, and who knows what, ash in a power plant there. Whatever, every process will be different. And so the ductwork has to be designed in such a way that the velocity is high enough that you don't get a settling out effect. That's the worst thing that you have is settling out. A typical, and I'm sorry, I'm an imperial units guy, and the typical number that you would often see in the the industrial world is 4,000 feet per minute. Well, that's a pretty ripping good flow coming down your ductwork. In the commercial world, if I recall correctly from my years of testing HVAC systems, you might have velocity as low as 1,000 feet per minute, more likely on around 1,500. And I think by the time you hit 2,000, you've got a pretty good flow coming through your ductwork. Well, the reason why this becomes important is because your pressure losses increase as the square of the velocity, and therefore the square of the flow value that you're trying to push through your ductwork. You have other things that come into play with this. I mean, people that are putting ductwork out obviously want to do this as cheap as possible. It's out of sight and out of mind. Things like this in an HVAC system, of course, it's above the ceiling tile typically, and you don't even see it. You have one of the things that ties into this very quickly, especially for HVAC systems, is that things like the velocity or the noise levels start to increase. And so now all of a sudden, if you try to make your ductwork too small, now you got to silence it. And if you silence it, not only do you have the pressure loss of this ductwork, which is under designed for the flow, but you've got a delta P across your silencer that you've got to worry about. And so, I mean, some of these questions that involve fan selection, well, add that to the losses that you now have to be accommodating here. One of the things, I mean, when you want to reduce energy and you got a blank piece of paper in front of you here, you want to minimize your pressure losses. And that means paying attention to two things: the geometry of all these connections and the ducting and so on. And then you also want to pay attention to the velocity. You don't want to have duct that's handling flow. I got into one system here the other day and I got looking at what these guys want to do, and they had velocity up in 7,000 feet per minute. Okay, wait a minute. This goes up is the square of the velocity. You know, let's just think about that. I mean, this is up to the point here where very quickly you might end up with 30% or 40 or maybe double the amount of pressure you need. Well, double the pressure, double the energy, double the power, double the energy, and so on. And I've already mentioned the last point. If it's in the industrial world, you want to meet what we call the minimum transport velocity. You don't want to go so low that all of a sudden stuff starts to settle out. Now, I have seen this done once where they actually do slow it down and things do fall out. And then once in a while, it goes through a purge cycle where they speed it all up, and they're doing it strictly for energy reasons. They got a purge cycle. Well, once something is settled down on your ductwork, guess what? It's like a lot of things in life. Once it's down there, it tends to want to stay down there. But that is something that I've seen done. Yeah, reduction of system losses. I've talked about what you can and can't do. I'm going to show you here. Let me just take this one here. So here's a square elbow, nothing fancy, 90-degree turn. Air comes in, air comes out. This is not a good way to design your system. Okay, you're going to end up with pretty high losses. Whereas if you put a nice round elbow in there, it's easier for the flow to come around. As a matter of fact, if you want to put, and I don't know if you can see that very well, but there's actually a turning vane in this elbow here. And so you're going to have a lot less. I use these in our fan workshops, Jay, in case you're wondering, and demonstrate how you can change system components in order to get a lot lower losses, and therefore you need less fan. You can slow your fan down that much more. This is the whole thing with the system approach, is that once you start doing this sort of thing, every one of these things reduces the required fan capacity you need. Maybe I'll show you this one here too. This is kind of you can see it's kind of got a smooth entrance here. It's got a rounded surface. So if this is on an entrance of a duct, then rather than the flow coming into a square edged orifice opening, you've got something that helps it get around the corner. And so you end up reducing entry losses with that. What else have I got here? Oh, I got one here I'm going to show you. And this gets back to this, what happens at the inlet of a duct. So let's assume you've got a round duct this time, and you've got some point that you've got a duct that's just sticking out in the middle of some place, and you're trying to bring air in. You know what? You're better off putting some kind of a bell mouth on that to help get the smooth, so the air can get around the corner and into the fan. And the other thing that often happens on inlets is they've got to put some kind of a screen on it. in order to keep the birds and whatnot. Now that's not going to, even this one here is not going to keep mosquitoes out and whatnot. That's for the filters, I guess. But this one here is what we call expanded metal. And I've seen this used out there instead of having fairly light duty screens that are still heavy enough that they would keep birds out. But I'll tell you, the pressure drop across an expanded metal screen is not good. Okay. And if you have that and you want to replace that with something like this and still put a wire mesh across there, you're gonna see a significant little pressure reduction as a result of doing that. Bottom line is you want to keep your velocities though where something that's reasonable out there. You don't want to go too, as soon as you go high, of course, as I say, it goes up as a square of speed. Avoid streamlined terms and condition. Avoid the shock losses, meaning the entries and the discharge. If you got a high velocity duct that's on the discharge, you just dump it straight out without putting some kind of a diffuser on that slows it down. And then issues of cleanliness. I'll touch on that cleanliness one again here in a minute. Okay, Jay. Yeah. Leakage and buildup. These are two things that are just different sides of the coin here. If you have leakage, you're moving air that you don't want to be moving. Let me just hit the draw button on here. So here's our normal point. You got leakage. What's the impact of that? Well, the impact of that is you're essentially are dropping your system resistance. But wait a minute, now you've dropped the pressure on this. So the pressure that you need to push the air where you want it isn't enough. So now you've got to accommodate that. How do you accommodate that? Well, in this case here, you've got a variable speed. So you speed the fan up in order to get into that point right there. So as I said, the buildup is just the flip side of this. What happens if you've got buildup? Well, now you've got your system resistance starting to increase. So now you're up at this point right here, okay, which obviously is a reduction in the flow that you're seeing your system. So how do you accommodate that? Oh, let's speed the fan up. Yep, speed the fan up. And so that point, by the way, is supposed to be right on top of that one. I've been lazy and haven't fixed that up yet. But both of these problems are solved with variable speed, which gets me into another whole issue that we'll chat about at the end, which is just about every problem you have out there is solved in a way that takes more energy. And both of these ones here are solved with more energy. So what you want to do is if you got leaks, then you repair the leaks. And we talked earlier here about infiltration and exfiltration, and knowing what the pressure is through the system is an important part of that. With buildup, well, you've got to keep your system clean. You can't have any buildup out there. I had this, I got a funny story to tell you, Jay. I promise I'll be fairly quick. I was doing some troubleshooting at a fairly small little dust collector in a light duty plant years ago, and I got into this place, and the fellow said to me, he says, I don't know what's going on with this system here, but we used to have enough capacity and we just don't have enough capacity anymore. And he said, you know what? It's a variable speed or a V-belt drive on. We've changed that speed a few times to get more capacity out of this, and it works for a while, and then we all of a sudden don't have enough capacity anymore. So he's telling me all the things here that are kind of giving me clues that I think I already know what the problem is. But I went in there and took a look at this fan, and this poor little fan, I mean, I don't know why it was still hung together, because it was supposed to be about 1,800 RPM, and this guy had it running at about 5,000 RPM. I'm amazed that he had enough motor that he could run the thing. But I ended up taking a pressure across the fan, just kind of like I've advised here at a few different points, is to know what your system is and get the pressure. And right across the fan, and we had 20 inches water gauge. I'm looking at this thing going, what's going on here? You're not moving any air, but you got 20 inches water gauge. And what had happened was, and if I'll just show this elbow here again, you can see this turning vane in here. This little dust collector had all kinds, it was like small little pieces of yarn that he was trying to exhaust. And these yarn pieces had kept looping over the vanes in a turning vane on the elbow until there was just simply no gap left in the elbow. And we came to the first elbow with the pressure, with a pressure meter, one of these, something like this. And, it was like 20 inches water gauge around the elbow. And I said, you know what? I think we found your problem here. Take that elbow down, clean the elbow up, and we're good to go. And that's what happens. And again, you got to understand your system and know what that pressure should be throughout your system in order to very quickly be able to diagnose that sort of thing. Okay.
We have this quick one on the MERV filters, but I'm able to jump forward to the questions. We'll leave this in the deck that we send out afterwards for reference after that. But we had a couple of questions from David regarding, looking at better air quality issues and recommendations to move to MERV 13. But what is that impact on energy consumption? And are there benefits to moving to? We've heard of some of those like smart air filters that are MERV 13 but lower, MERV 13 but lower pressure reductions, and if you see benefits with those.
Well, yes, the whole move to getting tighter and tighter on your air quality issues means having filtration that is just simply that more restrictive. There's no question about that. I don't believe actually, and I think that previous slide showed that, and we'll get into that with David, I think it is at another point here, but there isn't really that much difference between a MERV 8 and a MERV 13 when the filters are new. I think the one is maybe 25% more, but remember, it's only one part of the whole system here. So 25% more may sound like a bunch, but actually, if you're dealing with 5 inches and you're only going from 0.3 to 0.35 or something like that, that may not be all that much. Here's the problem with the MERV 13 is that as you get tighter and tighter with these filters, it means essentially the pore sizes in your filter are getting smaller and smaller. And that's what has to go, the air still has to go through your filter. And because the pore sizes are that much smaller, particles at the low end range of the size, and you're getting down into the 3 micron size, for the MERV 8, they might flow on through, but the MERV 13, they're now trapped. And so even though these filters may not have that big a difference in pressure drop in the beginning, you may find very quickly that the MERV 13 fills up and has to be replaced that more often. Now, the second part of this question, how can we get incentives for using that? The incentive part of that, Jay, I'll defer to that one to you because I'm not quite sure. From a mechanical perspective, all this revolves around doing some testing and understanding what's going on with your system and knowing something. I keep getting back to this low duty cycle because as soon as the filter starts getting dirty, the fan operating point is changing out here because now all of a sudden you need, for the same amount of flow, you now have to have the fan cranked up more to get to build the pressure to overcome the extra loss with this. So there's a bit of a study that I don't know that, on something fairly small like this, you don't want to start leading people down a path of saying, well, you got to study this, and it gets pretty complicated. But there really isn't, I don't think, an easy prescriptive answer I can give to that. It needs a bit of a study, and that kind of means trending and monitoring what's going on with your system and how much putting a smart filter system in there, which how much will that drop your pressure by?
And I did address some of the questions about the incentives in the chat there as well. So the next question from Edwin, and I think you touched a little bit on this with Alan's question when it comes to air balancing and maintaining that positive pressure. And it sounds like with Edwin's situation, they were told, well, those makeup air units have to run full blast all the time to keep that positive pressure. But are there strategies to save energy while still meeting that positive pressure requirement?
I'm not sure how to answer that one, Jay. You're into the whole question of how is the building controlled right now, and that one may change what kind of an answer you can give to this. There's one point. I'm going to take a very slight detour here, but there's one point I want to make with air balancing, and that is why do people do air balancing? People do air balancing in order to ensure that the space, assuming we're talking about HVAC, which I think when we think air balancing, we're almost always talking about HVAC, although it does apply elsewhere. But when you have air balancing that's being performed, somebody's going through and doing their adjustment at all the different points in the system to make sure that the correct amount of flow or the design flow that they were looking for is met at each one of the individual locations. that implies that they're measuring flow. And if you look at any air balance report, there usually is some, they measure all the different flows, and they may be doing a total flow, and hopefully the different sub ones match the total flow. Quite often they'll be putting in what the pressures are at these different points. Whether or not they're actually doing a delta P across the fan, though, is another question. Whether or not they're actually being able to locate those points on a fan curve and measuring the power at the same time, which would sound like such a small jump, in order to make sure that once you've got the air balance report, you also know what your fan efficiency is. And yet I've looked at a lot of air balance reports, and it's pretty rare to find somebody that actually bothers to include that number in there about what the fan efficiency is. Right. So I wanted to make that point about that. I view that as a real missed opportunity here with the air balance reports. That's the logical time to be doing that.
Yeah, and I think we've got to move on. We are running a little bit behind on here, but I think, we will have follow-up both on the Energy Manager Platform Forum, and, we can follow up with Vern afterwards on some of these questions as well. So getting into the increasing efficiency.
Okay, yep. Okay, so we've talked about ductwork and the need to minimize our pressure drops. There's this term that people more in the fan industry use, although it's not uncommon for some people involved with ductwork to know what this is, but it's something called a system effect. A system effect is not something that's typically regarded as a pressure loss in your system, but it sort of behaves a little bit like that, and the impact of it is put into inches water gauge. But what it really is, it's the amount of reduction in your fan capacity because of the way an inlet or outlet is designed. In other words, fans like to have nice, clean inlets coming up to them and nice, clean discharges leaving them. And as soon as you start putting elbows and other crazy things on your inlets or outlet, that fan starts to make it look like it just doesn't work quite right. And that means that it suffers a pressure loss or a pressure reduction in what it should be able to develop. This becomes a very complicated subject, but on the other hand, all you got to do is look at a few pictures and it starts to become obvious, and you too can become a system effect expert really, really fast. So let's take a look at this one that's on these pictures that it's on the right on your screen right now. So here we have two fans. And so this is a view for, actually I saw this first and I was so impressed by what I saw. I climbed up a ladder and took a picture from up above here. But essentially what we have are two fans blasting air right at each other. Okay. Does this seem right to you? You start wondering about it. So if one fan is just giving a little bit more flow than the other fan there, is it possible that that one could overcome that one to the point where one of these fans actually moves no air at all? It doesn't really matter. It's a hypothetical question, but what you have are two fans that are blasting air, and that air is expected to squirt out the side and make it over to whatever it's supposed to be doing over here. Yeah, you got two fans, they're pointing at each other and air squirts out the side. I mean, how can that possibly be efficient? The next picture is on the right. It's again there, it's the same fan, but from two different angles. And so you have a fan that's spinning in this direction here, and what you have is an elbow right on the discharge. So you may have a fan curve, and you might be doing some testing on this fan, and you plot your point on the curve, and you go, this fan doesn't look like it's working at all. And so what happens is, what do you do to deal with that? Now all of a sudden you've got a system where it's underserved. So if you're underserved with your system, you speed the fan up, you put a bigger fan in there, you do something, but it has to be accommodated in some way. Or in this case here, on what you have on the right, you say, okay, I think we're going to have to take that elbow off the discharge, put a long straight piece of duct in there. If we really got to turn that thing, then we'll do that further away from the fan. That's a little bit about what a system effect is all about. So the bottom line with this, for those of you who never ever run into this again, you want clean ducting coming up to the fan. You want nice, clean, straight ducting leaving your fan. End of issue. Causes of poor fan efficiency. I'll touch on the first one here, which is what was it overstated? And we're going to deal with that on the next few slides. Was there a better choice of fan? I'll talk about that on the next few slides. Is it operating at a poor selection point? Well, you're going to have a really, really efficient fan. You can spend a lot of money and worked everything out. You got the most efficient fan possible. But you know what? You can take the most efficient fan and run it at a point that's not efficient. It's sort of like having a car that gets incredible gas mileage and going down the road with your foot on the brakes. Okay, you can turn anything that's efficient into something that's not efficient. This point here about performance degradation, I'm going to deal with that one. I'm going to show you an example of that one in just a second here as well. But the bottom line is you have a hard time walking up to a fan and being able to say, well, I know how efficient that fan is. The only way you can do this is to test the fan. Okay, so fan efficiency is flow times pressure over power. So that means you've got to have a good flow reading, a good pressure reading, and a good power reading, and then you can make this make that determination. Okay, next. So here's our base case selected fan. What we have here is a fan that's got a system curve, and it's coming up through, and where the system curve and the fan curve intersect is where that fan is operating, and you can see bingo right underneath the best efficiency point. Life is good. There's a base case properly selected fan. Now this fan, you can see here on the scale on the right side, is 75% efficient. So you might have a fan that's at 75, or you might have a fan that gives you the same flow pressure relationship, but the efficiency is higher. Or you could have one that's lower. I'm going to show you two different fans here, and the ones that I have. And this is what we call a backward inclined fan. This one here, these blades are actually curved. And, you know, if this was a big industrial fan out there, you'd look at that one and you'd go, yeah, they could probably hit 85% efficient with that fan. Okay. So here's a much older style fan, which is a forward curve fan. And, you know, every furnace in the residential furnace that you see has one of these. And, you know, forward, a lot of blades in here, very short. This fan here, you would be hard pressed to find one of these that's over about 65% efficient. So then that starts begging the question, why would you use this fan instead of this fan? And that's when you start getting into a whole bunch of application issues. If you were to use the more efficient fan for a furnace, that furnace would have to be about double the size of what it is right now. And so you start running into those kinds of considerations and application issues that make this determination of one for another. So a little bit of thoughts that kind of also address questions of fan selections and what kind of fans that you have out there. Okay, one more I want to show you here. Give me this one right here. So this one here is something called an axial fan, which is a completely different fan. One of our guys in our office made this little mock-up, and it actually did a pretty nice job of duplicating a scale model of a real mine ventilation fan. This kind of a fan behaves different. The other ones, the flow comes in and goes out at 90 degrees. And this kind of flow comes in and goes out. But you know what? You can select this kind of a fan and also be able to achieve efficiencies in the 85% range. I'm going to hold that thought though, because the next slide, I'm going to make that point. You can see with the problem with this fan here is that because the system resistance is much lower, you're moving a lot more flow, but you're doing it at a much lower pressure. Well, if you go back to your efficiency curve, what you can see here is that that efficiency is in fact dropped quite a bit from where the peak was. One of the advantages of axial fans is that, and I've got to speak very generally here because, you know, I'd soon get taken to the cleaners if I tried to be specific on this. But one of the advantages of axial flow fans is that they're much better at moving this whole curve off to the right here so that you can, once again, get your best efficiency point to line up with your operating point. Let's go to the next slide, which is the reverse of this one, which is a system resistance, which is now much less than than where it was originally when we were sitting under the best efficiency point. And there's a few points I want to make with this. Not only is our efficiency down quite a bit, but as soon as you start going over to the left of the curve, you start running into an unstable region there where the fan could start pulsing away. And I'm going to show you an example of that a little bit later on. Okay, next one, Jay. This fan is one where it's on a system curve that goes right up through a point up here, which is under our best efficiency point, but we're not needing that much fan. In fact, we need substantially less. So we got the fan dampered well down. And in dampering that fan down, its efficiency has dropped like a rock. So what we have here is a fan that is just simply way too big for the application. Now, you got to be really careful. This is where you have to really know your system, because if you do what we've suggested in this case here, which is get a different fan in here that's sized more to go down through that point instead of the original fan, which was, you know, way up here, do we really know enough about this system to know whether or not this system doesn't have upset points where it really is needed out here? And this is where you start getting into things like variable speed and whether or not the variable speed can slow it down and satisfy both worlds. And that's one of the big advantages of variable speed, is that you can be quite efficient at different points. The efficiency doesn't change no matter where you are along our system curve. The problem with this, though, is that not every system quite behaves this way. You know, you can have systems that instead of that blue line down here, it's up here someplace, or a constant flow situation where the system curve is out here. So you can run into those kinds of questions. That takes it to quite a much more complicated level I can't deal with today. But so we'll move along with that, Jay. And but just know that you got some issues there. Now, can I have that cone right here, Pankaj? Yeah. So.
And let's maybe quickly touch on these so we can get to some of the questions on this, which I think touch on some of these issues as well.
So this here is a fan that's degraded. I've talked about that. Now, this cone is not sized for this wheel. This cone's too big. But ideally, that cone should just fit right inside that wheel. You know, this becomes the non-stationary and this is the stationary. And as soon as that happens, that, you know, you get a wee tiny bit of leakage. But what happens, and I've seen this happen, and this is a real maintenance issue, somebody changes the bearings on the fan, they put this thing back together, they have problems nesting that thing so that it doesn't start hitting, and so they leave it back. And as soon as you start leaving that back like that, just like you see in our picture here, you've got a gap, and with the gap in there, you end up with recirculation. So you ultimately at that point end up with something where the power looks high and the flow pressure here is low. And that's what happens. So, you know something about this, because if you're doing and you have something to do with maintenance, or if somebody's done maintenance on your fans, that may in fact be something that can happen quite easily. Fan manufacturers spend a fair bit of time to make sure they've got that gap right, because that is one of the main things they have under their control when they're making that call on how efficient a fan and whether a fan can meet the curve. You're just looking at a picture of some fan that I saw in the field. You can see just a quick point on this, that edge of the stationary part, typically in most applications is about halfway across that part of the impeller. And you can see they've left a pretty good gap in here. And that gap is where you end up with the internal leakage. Now, this is one of my favorites. So in recent years, we've seen folks sell this device, which is some sort of a thing that fits right into the inlet cone of a fan. And this from our fan model that we use for our workshops. And I did some testing in the shop with this one day and found very quickly that when these guys start putting things like this into the inlet cones, it kills the performance of the fan. I mean, you'll knock 10% of your flow capacity off your fan. Maybe not as much if that fan was a bigger fan, because that's is sized for it's kind of small for that particular fan. But hey, listen, if you drop your flow by 10% and you've got a variable speed drive, what do we all know about what happens when you speed a fan up? How does power happen? Well, you 10% more, you got to go up by the cube of that. So 1.1 times 1.1 times 1.1 is what your new power is. So you're at 32% at that point, all because of this kind of a device. Now, there's no reason why you need that kind of a device. There's other ways to measure flow that don't kill the capacity of a fan. Okay, Jay. And I think this is one of my last ones. The issue of performance tolerance. This is a huge industrial issue. It perhaps doesn't get as much attention in the commercial world. It's not something that we see talked about too much. But here's in a nutshell, the issue. And that is that everything that you measure has tolerances around it. So if we're measuring a fan and we're measuring it with the best equipment and everything is ideal, you still have a tolerance on your number here of plus or minus 2% on flow, plus or minus 2.5 on pressure, and your power might be within 3.5. Okay, so while you're looking at those numbers, I want you to think back. Okay, efficiency is flow times pressure over power. So what's the impact of this on the efficiency if we are arguably at the low end of the tolerance for flow and pressure and the high end of the tolerance on power? Oh, and oh, by the way, I did tell you that this is our minimum uncertainty. That means sort of the best that test you can do. You start getting into the field sometimes, and we've seen this happen where a fan manufacturer will quote, oh yeah, we'll make the capacity and the efficiency of this fan here, provided it's tested to the maximum uncertainty of the AMCA publication 203. Go to the next slide and let's see what the impact of this is. If now you're going to go low on flow, low on pressure, high on power, the best test that you could do says that your efficiency could be down at as much as 8%, and that fan deemed to have passed. If you go to the worst case, your efficiency could be off by 23%, and it still is deemed to have been acceptable because it met the acceptance criteria. I think I touch in that in one of the documents, Jay, and I don't know if that one got passed along. I think it might have, but you know, if anybody doesn't understand this, by all means, give me a call, because we've written papers on this issue, and I'll be more than happy to share some of that. Part of the problem with this is in the commercial or in the industrial world, we're going to test fans. We're going to have performance guarantees. We're going to do all kinds of things, hopefully, to make sure that a customer gets what they paid for. In the commercial world, it gets a little harder than that because we're not dealing with fans that are $500,000. They're fans that are maybe 20,000 or 50,000 or something like that. So it starts to become this bit of a disproportion on how much you can actually spend to deal with that. Okay, how do you specify the right fan? I kind of walked through that. You got to deal with your flow first and make sure that you know what all your worst case scenario is, where you typically operate, where the whole range of what you need with that. You do have to satisfy a worst case with this. And then you got to work through all your hardware issues and work out what the pressure drop is. And you might want to play with that and spend a bit more money to try and keep that pressure drop lower, but then you get a fan spec. How do you determine if the fan was sized properly? I'm assuming we're talking about an existing fan. If it's a new fan, that maybe gets a different answer. But if we got an existing fan, you can't walk up to a fan very easily and kind of go, yeah, efficiency is that much, capacity is that. You got to test it. And so the bottom line with that is it's pretty hard to make any kind of a determination with that without doing a field test. Doing a field test, here's a pitot tube, pretty inexpensive. Here's a manometer here, a pressure gauge that is suitable for between the pitot tube and this. You can soon start measuring flow. And if you need help on that, give me a shout, okay? None of that equipment, I mean, within a few $1,000s, a person can have performance testing equipment. Some of that maybe not really high level equipment, but there's you know, people want to sometimes just get to know what the rough and dirty performance is of their fan. They're not trying to satisfy a performance guarantee that's got penalty clauses with it. Let me know if you need any assistance with that, and I can answer that question a bit more thoroughly as well. For small applications, I recommend VFDs or ECMs. Well, both of these give you variable speed capabilities. ECMs, I know that with ECM motors, they're also pretty efficient motors out there. And even without the variable speed, people tend to use them. I don't know that I'm real qualified to answer it too much beyond that. I've got a 1 horsepower VFD here. I've got a pretty good idea of how well that works. It does a very good job, and it drops our power down just about as it would be expected with the relationships of speed and power. I'm not sure that beyond that, Darren, I know how to answer that question. I'm a little bit out of my field with that one because this is dealing with very small motors, not large ones.
And I think one of the things we've heard on that is making sure that it is an application that will ramp down as well, of, you know, putting a VFD or moving to an ECM on a system that has relatively consistent flow demands. Not so much, but we've seen applications, you know, smaller HVAC applications, but if there is that variable demand, it can still have quite good savings on there.
So the business case for high efficiency cog belts, we know one thing, and well, I'll give you a rule, my rule of thumb on this, and my rule of thumb is that a cog belt has about half the mechanical loss of what a traditional V belt is. So if a traditional V belt was 95% efficient, a cog belt is about 97.5. Or if they started off lower than that, which may be the case for smaller equipment, the smaller the equipment, the more inefficiency you have with V belt drives. You get down to a 1 horse motor, I think the inefficiency or efficiency of one of those belts is probably not much better than 75% or something like that, or maybe better than that. I'm not sure. It's not that easy a thing to measure, frankly, to know. And then, of course, it's a variable because as soon as the belt is installed, then the tension on it changes and geometry changes a bit with wear and so on. So it's a variable thing. But I think that would be generally the case. Cog belts have less wear. Obviously, they're not going to start slipping. Business case for this, you know, essentially you're looking at it when you say business cases. What my costs are to run it versus what my cost is to install it, and what my cost would be after it's installed, and therefore what my payback is on it. I'm going to guess that cog belts probably have reasonable paybacks, but clearly the time to do it is when you've got a worn out belt that you need to replace. And by the way, it's not just the belts that end up being worn out, it's the shivs as well. And I've seen shivs that end up being so worn away over a period of time that eventually you get to the point where, you're gone. You got to put a new shiv in. I mean, would I make a recommendation of removing shivs and belts and replacing them with cog when these are brand new still or in good condition? Probably not. I don't think so. Okay. One thing you do have to watch out with cog belts is that you might end up with a noise problem, and that's one of the things that you can run into. There's a high-pitched noise. It's kind of a pass frequency on the cogs and so on. So that's something that you may have to watch. Inside an HVAC or an air handling unit, there's enough insulation and other stuff that's probably not an issue. So maybe it's more of an issue if you've got a freestanding fan someplace.
All right, so we've got about 7 minutes left before we wrap this up.
Oh,
so
okay.
Maybe we'll get through some of the tips of energy managers, what they can do to identify where these opportunities might be. Then we'll do our quick wrap up, and if there's anything else after that, we can see if anyone wants to stay after.
So we're just looking at here how one walks through a process of screening, audit, feasibility study. Each one of these cranks it up, and validation being that one at the end here, which is in many ways the most important one, where you're proving that in fact, what you came up with the calculations on something actually works. So validation implies that you've conducted performance testing after you've done to verify that in fact it's working. If you go to the next one there, I think I talk a little bit about screening and what's involved with this. So we're consultants here. So we look at stuff from the lens, through that lens of being consultants. So before I go on a job site, quite often we're getting the phone calls going and the emails going on, okay, how old is this facility? What do you make? How many fans you've got? What are the products? What are the operating points for these fans? Do you have fan curves? Do you have fan drawings and so on? And that's all stuff that we want to kind of see laid out before we get onto the job site. Once we're on the job site, you want to inspect this equipment. You want to walk from one end to the other. This issue of pressure drops, you're never quite sure until you get onto the job site where you're going to find that. You're never quite sure on the job site where you find out issues that pertain to the flow utilization and whether or not it makes sense what they're doing with the flow, or whether or not you run into applications where you're wasting a lot of flow. Okay. Tips for energy managers. Okay, so this will kind of summarize a few different things I've said so far. Fan power and energy relate directly to pressure and flow. Remember, pressure times flow divided by efficiency and time. All those four things are, so every one of those has virtually identical impact in terms of how much energy you have or how much energy you could reduce it by. If you're looking for fans that are good opportunities, look for ones where the inlet dampers are significantly closed. Okay, I showed you that one example with a fan that with way too much margin on it. And so if you've got dampers that are quite significantly closed, you know, those are likely good opportunities. Maybe variable frequency drive opportunities, maybe smaller wheels in the side of fan. There's more than one way to deal with some of those kinds of issues. Fan mechanical problems, and if, I don't know, Jay, if we're going to have time to go through some of the case studies, but if we do, but that is centered around fan mechanical problems and reliability issues. I'll just say as a lead into that, if we get there, and that is that just about every time that we see a fan problem, we usually see an opportunity to drop energy requirements. I mean, there's very few problems in life that you don't solve that don't require more energy. It's too cold in the building, turn the AC on, more energy. Too hot in the building, turn the furnace on, more energy. Okay, every problem out there ends up having some sort of a solution that revolves around energy. Okay, so get the performance curve. I said at the beginning here, life gets miserable for you out there to try to optimize much if you don't have a curve, and that's because the curve tells you so much information on what you have right now. And then as you go through the system, get a little bit of data, get some pressure data. If you can, get some flow data. Getting the power data is not too hard, at least on HVAC systems, because with electrician and opening up the panels and getting the volts and amps, and you can relate that to sort of how heavily loaded motors are and so on. So you can get a bunch of that related to curves. Okay, whereabouts are you on the curve? Are you on a way to the left or the right? Are you kind of best efficiency? Pay a lot of attention to these leakage, recirculation loops, throttle dampers. One thing I want to mention, and this is an opportunity that I've seen many, many times, is when somebody has designed a system where the fans have multiple users. Okay, by multiple users, a user, I'm not talking about a person, I'm talking about a different aspect of a process. But it's being asked to deliver air to this part of a process and that part of a process. Well, not all these processes may need the same amount of pressure. If you don't need the same amount of pressure, guess what the fan has to do? Fan has to crank up the pressure to supply the part of the process that needs the most pressure. That's what it has to do. Because if it doesn't do that, then we got at least one process that's not satisfied. And as for the rest of the ones that need less pressure, well, we use a throttle damper in the system to knock it down. So those are opportunities where you might be better off with more than one fan. Each one of these processes might have been better off having its own fan. Yes, pay attention to systems that have changed from the beginning. It's not uncommon for us to walk onto a job site and kind of go, I don't understand. This fan is not at all suitable for this process at all. It's just, well, we made some changes over the years. And that happens no matter what it is. HVAC systems, happens all the time. It's one constantly changing thing out there as space is redeveloped and users come and tenants come and go out of the space with their different needs and so on. So I think that just about does it there, Jay, as far as some tips to drop off with the energy managers.
All right.
How are we doing on time here? What do we got?
Well, it's about time to wrap it up. So I think what we might do is we'll do our quick wrap up here, and then maybe we can talk about one or two of the case studies if anyone
Sure.
is able to stick around after the fact on here. So next steps, as always, we really appreciate your feedback on these workshops. Helen will place the link to our feedback form in the chat, or if you're using your phone, you can use the QR code that's on the screen now. So please take a minute or two right now to fill out that feedback form. As I mentioned, we really appreciate that. So we'll take a quick pause now to get your feedback on it. It's only a couple questions. It's really short. While you're doing that, I do want to mention that we will keep this discussion going. I know we didn't have enough time to get to all of the questions that were submitted, but we will be following up on the Energy Manager Learning Platform discussion forum. We'll start a thread there addressing some of the questions that we haven't yet addressed, and we'll get Vern's input into filling those out. And a reminder, the URL to get to that is emss.goldfin.ca. If you don't have the login for that, you get it by registering for Energy Manager Support Services, which is a free service provided by the Save on Energy program by the IESO. So you reach out to us if you don't have your login information, but then you can access that for those questions. So thank you for taking the time to fill out that feedback. One last reminder about the Energy Manager Awards. Really looking forward to seeing everyone in person. If you haven't registered yet, please do so now. The space is limited, and I'm really looking forward to an exciting and great event, celebrating and learning about some of those key success factors. And we have one last Menti question to go to. So once you're finished going to the feedback form and filling that out, please go back to Menti on your phone or browser. Either if you lost that, you can go back to the QR code or go to menti.com and enter the code. Helen will also put the link in the chat. And we have one last question for you to answer, which is please share with us what's a key takeaway from today that you're going to be looking to apply in the next week or two or something shortly. But what is some action or takeaway from today from Vern's responses and knowledge sharing that you're excited to apply in your facilities, in your systems? So if you can take some time to fill that out, and we can take a look at those. While people are filling out this last Menti question, Vern, do you have any parting thoughts to share?
Well, I mean, the main one is I know I've ripped through a lot of stuff here. It's a difficult thing to take so much material and kind of jam it down because we're trying to kind of hit on all the different key points. Please give me a call if we can help answer any questions or if there's anything specific, or shoot me an email or whatever if you want my opinion on something with this. I always like, as I say, to try and hit a bunch of things with one approach out there. And once one goes down this process of energy optimization, the other parts to this is making, I mean, optimization can mean a lot of things out there. And some people will think that optimization means that I've got enough capacity for my process. I've optimized that. And that is one form of optimization. The next person's optimization is, I want something completely reliable. Right now, I don't have this thing that's reliable, and I got to lay awake at night and worry that the next phone call is going to be one getting, oh, get in here, this fan just failed again. And so optimization means all of those different things, and there's no reason why looking at a fan you can't deal with more than one aspect of this. If you just look at the energy part of this, chances are you'll be somewhat disappointed. Okay, it's possible you can just deal with energy, but you really need to be looking at the overall picture with this to make sure that all these other things are satisfied as well. First thing that I do when we start a project is I want to first deal with the production people, make sure that I fully understand what the production people has. If you're dealing with HVAC, you want to know things like, is there any parts of this building where you just can't get the temperature down to where it's supposed to be? If you're dealing with the maintenance, the second group is the maintenance people. Which fans are the least reliable ones here? If you're going to make changes with fans to reduce energy, you may as well knock off these other problems at the same time. I think that's my parting comment with that. It's optimization of this. Energy is one part of this, an important part of this, but you know, if you focus on that, you're losing an opportunity to take other problems away as well.
Great, and I see a lot of stuff in the responses in terms of, you know, taking some of the advice of getting those performance curves, reviewing recent balancing reports, starting to gather that information and making sure that, you know, when people are starting to look at their fan systems, that they have the information and seeing what's going there, looking for blockages, sharp turns that impact pressures, fan ducting maintenance. So I think there's some really good takeaways in here. I want to thank Vern for being our resident expert for today for this Q&A. I want to thank everyone for participating and submitting your questions and taking the time today to join us. As I mentioned, we will be, you know, looking at the Learning Platform Forum and others to address those that we didn't have a chance to get to, so we apologize for those, but we haven't forgotten you. We will get to you. So again, thanks everyone. This does bring us to the end of time for today. So we look forward to seeing you next time. And I think maybe we might backtrack a little bit and maybe take a look at one or two of those case studies for anyone who has the time and is interested in sticking around for that. Otherwise, we will be providing both the materials that we've covered and didn't get to, as well as the recording. So you can take a look at that later as well. So thank you again, everyone.